So what we're going to do today is to kind of zoom out slightly from the breadboards and think of the breadboard for one of whatever we build on it. They have one or two inputs. Okay, most of them will have two inputs, but the NOT gate only had one input. So got a thing that's got a couple of inputs, and it also has an output. So yeah, there was a lot of parts there. There were lights, there were wires all over the place, right? But zoom out and think of that breadboard as just being a single thing with two inputs and one output, and that's it. Okay. Then we can start to think about, well, what are the different, well, two things. What are all the different breadboard units that we could build? And then more interesting, what happens when we start to combine them and use the outputs from one or more of them as inputs for others? Okay, make sense? Okay, so the three gates that we built, well, built and or talked about, right? We talked about the first one was an inverter, right? And it had one input and one output, and all it did was take the input and flip it to be the opposite. Okay, so not particularly exciting, but that's what it was. And all of these symbols, by the way, have, or all of these gates have symbols to go with it. Okay, and so for example, the NOT gate is this symbol. It's basically just a triangle with a little loop at the end of it. Okay, and the little loop at the end of it is always going to be, whenever there's the word NOT in the name of a gate, it'll have that little loop at the end of it. Okay, so this symbol represents the entire breadboard that had the NOT gate on it. Okay, is that all right? And what was its truth table? Okay, so let me actually turn, let's do, say, 45 pixels this way and 45 pixels this way, and I'm just going to make some tables, okay? So the NOT gate, oh, and let me blow up the font so that you guys can actually read it. Oops. That ought to work. Okay, so the NOT gate, its input, I'll do this. I'll use A to represent, A and B to represent the inputs, and O to well, maybe O is not the best because it looks like a zero. Well, I'll just say out. How about that? Okay. So what are the two different patterns for the input on a NOT gate? There's only one input, so it could either be a, yeah, 0 or a 1, right? And what is the output corresponding to each of those inputs? It's the opposite. So if I get 0, 1 in, I get 1, 0 out. Okay. And the symbol for that is this guy here, the little triangle. Okay. And I can demonstrate this if, for example, let's see, I'll do input output. I'm going to put a little switch here. I'll do an LED. Okay, so this program I'm using is called Logisim, and it allows me to simulate basically putting these things together. So think of it as a big collection of virtual breadboards. All right, so I've got this little switch here, right? And if I flip the switch to being on, then you see this wire turns bright green. Bright green in this program indicates it's on. And then what's the output on the LED? Off. And if I turn the switch off, what's the output? Turns it on. Okay, so it's always the opposite, right? Okay, so that's cool. Then let's look at the two other gates, one of which we built and the other of which we haven't built yet, or you guys haven't built yet, but you will. We built a NAND gate, right? How many transistors did that take? 4, 2 P's and 2 N's. We also threw some lights on there to just so we could see what was going on. The lights themselves are not really part of the circuit. So imagine just if all you did was pull all the LEDs off of the breadboard, what's left is itself is the NAND gate. We put the lights on there just so that we could make sure it was doing what we thought it was doing. Okay, so the symbol for a NAND gate is this. Okay, so I'm not very good at drawing these things by hand, but the pattern is the word "and" always has flat, straight line back. Okay, so here we've got, you know, a little semicircle looking thing and a flat back. And then the pattern is anything with the word "not" has a little loop at the end of it. Okay, so an "and" gate is this same symbol without the little loop at the end. Okay, which is kind of nice. Okay, so got that. And how many inputs do I need this time? I need 2, so let me configure my switch panel to only have 2 switches. Okay, it's got 2 inputs, and so I'll put this one here, and this one here. And then I'll also put an LED here just so we can see the output. Okay, all right, so what was the pattern, or what was the table that we built with the NAND gate, right? What was its truth table? So let's just put that over here and say NAND. Okay, first off, how many different input patterns were there? There are 4, right? Because, and let me make, I'll shrink this a little bit so it fits in the box. Yeah. All right, so let me just say NAND gate. Okay, so I'll put A on the top and B going down the side. There were 4 possible patterns, right? 0, 0, 0, 1, 1, 0, and 1, 1. Okay, well, let's just figure out the truth table by flipping the switches here. But do we know what it's supposed to be from the get-go? So what was it supposed to be? And then we'll test it and make sure that we're right. When was the NAND gate's output light off? When both inputs were on, so we had a 0 here, and otherwise, what was the output light? On. Okay, so that should be our truth table. And let's check it. Right now, I have input pattern 0, 0. Is that a 1? Yes. Okay. 1, 0, 1, 0, 1, 1, and finally 1, 1 gets a 0. Okay, so we've got the correct table here. Okay, good. All right, and then we didn't build it yet, but we talked about it, which would be the NOR gate, right? And in terms of the transistors, what was the secret sauce for that? How were the transistors for the NAND gate? The P's were in parallel and the S or the N's were in series, okay? In a NOR gate, the P's are in series and the N's are in parallel. So it's sort of flippied in some sense, okay? And what was the truth table for it? Okay, well, we didn't build it, so we maybe don't remember it, but what is the truth table for OR? Yeah, so when is the OR gate going to output on? When either input, possibly both, are on. And this thing is going to do what? The exact opposite of that. Okay, so its truth table, well, let's just wire it up and see. Okay, so let me just, oops. Let me copy this. And then let me get on the, let's see, gates. I want a NOR gate. Fire the two inputs. And let's get another LED here. Okay, so both inputs are 0. What's the output? It's a 1, okay? And then if I flip, oops, 1, 0 becomes 0, and 0, 1 also becomes 0. And then finally, 1, 1 becomes 0. Okay? Oui ou non? Okay. So the pattern here, notice that the or, anything that has the word or in the name, instead of having a flat back, it has sort of a rounded back. And again, I'm really terrible at actually drawing these by hand because, well, I became a mathematician, not an artist, for a reason. Okay, so what would happen if I wanted an AND gate, say? I want this gate, which is the AND gate without the sort of loop on the end, okay? How am I going to build it in terms of transistors? What would I have to do based on what we breadboarded? I'd have to build a NAND gate first and then tack an inverter on the end of it. Okay, so let's build that sort of digitally here. All right, so I'll take a NAND gate and then I'll also take an inverter and I'll take the output from the NAND and make it the input from the inverter. All right, let me copy the little switches down. Okay, and then also a nice LED here. Okay, and we'll put this right below. Oops. Okay, now let's just use our heads. What should the truth table be for the AND gate? There's two ways to think about this. Sorry, I heard something. Yeah, it's the opposite of an AND gate, so that's one way, but by just definition of it, that's one way to think about it. The other would be just, well, what does the word AND mean, right? How is an AND statement true? Both of the two inputs have to be true, and otherwise it's false, okay? So it would be this, which notice is exactly the opposite of an AND gate, right? So either way you think about it, we get the same result. Okay, does that make sense? Okay, now let's double check it, of course, with the switches. So you can see this wire right there that's between the NAND gate and the inverter is the output of the NAND part, and then that's the input for the inverter part, right? So that's one reason I like this program, because it you can kind of see what's going on. All right, so let's flip the switches, and what do we got? All right, so 1, 0 is 0, 0, 1 is 0, 1, 1 is 1, and 0, 0 is 0. Okay, so we're good. Okay, now if we did the exact same thing with a NOR gate instead and tacked an inverter onto the end of it, then what would we get? An OR gate. Okay, and based on what we just deduced, what's its truth table? Should be the opposite of the NOR gate, which would be this. Okay. Does that make sense? Right? And we can wire it up the same way. And let me put this, so that's the Nand gate, followed by the inverter is an AND gate, and that's a common enough thing that we have a special symbol for it. But look what it is. It's the NAND gate without the little loop on it, okay? The OR gate, by the way, if I can build a, oops, wrong one. If I could build a NOR gate and I can do an inverter, that's equivalent to doing an OR gate. Okay, so just like with the NAND. Is that okay? And let me scroll so you guys can see it a little easier. Okay, so that's good, right? No. Okay, now we get finally to a more interesting gate. So let's take the OR gate for the moment and looking at its truth table, okay, how does this relate to our, the word OR in English? Is this the sort of regular meaning of the word OR in English? Yeah, okay. What's the other meaning of the word OR in English? Yeah, the exclusive sense. You can have one or the other, but not both. Okay, and that would be its truth table would have a 0 in the bottom right instead of a 1 in the bottom right. Okay, so are you in math or computer science this semester? You would all answer yes, because you're sitting here in the room. Maybe some of you also are in a math class. That's cool. Maybe some of you ain't. Doesn't matter, right? But if I ask, like my mother, right, do you want apple or cherry pie for dessert? What's the implication there? You can't have both, okay? So that gate, we need to think about how to build it, okay? And there are a number of ways to think about it, but maybe one of the easiest ways is just to word it out in English and then match the logic to it, okay? So exclusive OR means one or the other, but not both. Yeah? Okay. So we'll kind of write that out. Okay, so exclusive OR, which we'll put here, or actually I'll put it on this side. Okay, here's the desired truth table. Okay, that's what we want to get out of it. Okay, because it is one when precisely one input is on and the other one is off. Okay, so one or the other, but not both. Okay, does that make sense? So let's kind of dissect A or B, but not both. Okay, now that's a statement in English. It's sort of logical, but not quite yet. Okay, what does not both mean? Okay, so let's dissect this. A or B means A or B. Not both, what's another way for me to say that? Hmm? Yeah, exactly. A, NAND, B. Okay, and but means, in this case, we require both things to be true. A or B has to be true, and it can't be both of them. So the but here is really and. Okay, and so I can rewrite this in the following way. I can say A or B and A NAND B. Okay, does that make sense? Well, better late than never. Okay, so, oh, and let me scroll it up so you guys can see it a little bit better. There we go. Okay, so does that sort of how we took it from English and kind of made it a more quasi actually logic statement make sense? Okay, all right. What's brilliant about thinking about it this way is that it gives away how to build it. Okay, so I've got in parentheses there two things. I've got an OR and a NAND, right? Do we know how to build a NAND gate? Yes, you already built it. Do we know how to build an OR gate? Sort of. We haven't built it yet, but what are we going to do to build it? What's step one on an OR gate, or NOR gate, excuse me, right? So I could build a NOR gate. We've got the diagram for it, right? Can I tack an inverter onto the end of that? Yep. Okay, congratulations, you have an OR gate. We already built a NAND gate. And so what's the only other gate that we need here to pull this off? What's the in between the parentheses? We need an AND. Okay, well, how do I build an AND gate? First, I build a NAND gate, and then I build an inverter on the end of it, okay? And I'm going to use the output from the things in parentheses to be the input for this other circuit, or for the AND gate. Okay, so you guys know why there are 3 breadboards in your bins? Because you're going to do precisely this, right? You've already built the NAND gate. So what's the next step? Build an AND gate and an OR gate with the lights and everything. Make sure that individually all 3 of them work the way they're supposed to. And then the piece de la resistance is to put them all together. Yeah? That can be awesome? Okay, so let's sort of schematic put it together. Okay, so we need an AND gate, which let me do it as a NAND gate plus an inverter. Okay, and I also need an OR gate, and how am I going to build that? As an OR gate plus an inverter. Oops. And I need to put this here. And I need a NAND gate here. Okay, and then let me get my switches on here. Okay, so input 1, input 2, input 1, input 2, output. And then finally, I'll put the LED here. Okay, so that contraption is essentially what you guys are going to build. Okay, so what are the different pieces here? This is the NAND gate. You've already built it. Okay. If you can build one NAND gate, can you build a second one? Yeah, just duplicate it, right? And then you remember when especially those of you that I was working with how we left a bunch of space between all the transistors and the output LED on our NAND gate? Why did I leave all that space? What does having that extra space allow you to do easily? Yeah, that extra space I put there so that there was room to put the inverter in. Okay, is that okay? All right, so on one breadboard, you'll have your NAND gate as is. You don't have to touch that one. On another one, you're going to build another NAND gate and then tack the inverter on. And then finally, you're going to build a NOR gate and tack an inverter onto him. Right? Okay, so build each of the three of them individually, one on each of the three big breadboards. Yeah? Okay, once you've done that, and also include the LEDs and stuff, right? We'll make sure that it actually works, each one individually, and then put them together. If you try and do all of this at once, you're going to drive yourself crazy. Okay, so does that make sense? Yeah, so there you go. There's the, guess what you guys are going to be working on for the next few days. Yeah? Okay, now, two things. How many transistors is it going to take to do this? A lot. How many will it take for the NAND gate? 4. We already did that. How many is it going to take for this NAND gate? Another 4 plus the 2 for the inverter, so we're up to 10 total. And how many is it going to take over here? Another 6, so we're up to 16 total. How many of each kind? It's always in pairs, right? So you're going to have 8 P's and 8 N's. Okay, now, if your bucket does not have the requisite number of parts, please let me know. I have a bunch of extras so I can put them in. Now, in terms of the lights, how many are you going to need here? 9, right? 2 inputs for each circuit and 1 output for each circuit. Although later we'll remove 2 of them because they'll be redundant. Okay. Therefore, you also need 9 330 ohm resistors. And are there any other components you need other than a bunch of wires? Nope. Okay. So the last thing would be when you put this stuff in the bins, right, or take them out, put sticky notes or something on each one so you know which gate is which, right? Because you can't just put the whole contraption into the bucket at once. It won't fit. You're going to have to take things off, okay? Now, the last question, this is important, and this is the one maybe downside to this simulator. Does it ever show us where we have to plug in plus 5 volts or ground? No, they're kind of swept under the rug and assumed that necessary power and ground are there. But we do need that when we actually build this stuff on the breadboards, yes? Okay, so how am I going to get power and ground to 3 different breadboards when there's only one plus 5 volts plug on the Arduino? Yes? Yeah, exactly. If you've got a plus 5 volt rail on one breadboard, you can plug the other one into it, and it will also therefore have plus 5 volts. Same thing for the ground pin. Okay, so you have to kind of daisy chain the breadboards together for the plus 5 volts and for the ground, and also, by the way, for the inputs A and B, right? Okay, so now you don't need to worry about that right this instant, because what's step 1 is to build each of these 3 things completely separate from each other. Okay, in which case there's at any one moment only going to be one breadboard in question. It's only once you verify that all 3 work correctly that you're even going to think about putting them all together. Okay, because otherwise it will not be pretty. Okay, does that make sense? We okay. So the last gate that we could throw on here if I can do XOR, what could I throw on the end of that gate? Well, I can throw an inverter on it and have in XOR. Yeah? Okay. So, I mean, that's maybe not particularly gloriously interesting, but I can do it. All right, so this was, sorry, XOR gate. And then here I want the in XOR gate, which is going to be, guess what? The exact opposite of the XOR gate. So you see how it's flipping? Now, you might look at that and say, why on earth would I ever need such a gate? Look at its truth table and maybe you can see why it's useful. Okay, so think about it for a second. Right? Okay, so what does that maybe tell me about the two inputs? They're the same, right? So this gate is capable of doing equality checking, right? And that turns out to be kind of useful in a computer, right? Being able to tell whether or not two things are equal, you can just in XOR them. And if you get a 1 out of that, then you know that the two inputs were equal, right? And if you don't, well, they weren't, okay? So these 7 are all the 7 fundamental gates. And for that matter, any other gate, so here's sort of an interesting mathematical question. How many total theoretical gates could we have? That have 2 inputs. Let's restrict our attention to that. Yeah. Okay, so let me, that's a good point, Joe. Let me rephrase. I've got truth tables here, right? If I imagine, I'm asking how many possible truth tables are there when there's 2 inputs? 16. How did you get 16? It's 2 to the 4th, okay? So here's the way to think about it. In each box, how many choices are there? I have 4 boxes, each of which could either be 0 or 1. Does the value in one box determine the value in any of the other boxes? No. So these are independent choices. And so this question is equivalent to asking, if you flip 4 coins, how many different possible patterns are there? 16. 4 coins, yes, not 2 coins. Yeah, so 4 coins. So how did I get that? The first coin, how many choices are there? The second coin, are they independent of each other? So the number of possibilities multiplies, then times another 2 times another 2. So there are 16 possible 2 input gates. Now, why do I only have 6 up there? There's 2 reasons. One, some of the other ones are just not useful, or they can be built out of these 6, right? So why talk about, make a whole bunch of extra gates or names for them when we could build them out of these primitive components? Yeah? And there's maybe one of them that I could throw on there that's useful, but I can build it out of others, which is called the implies gate for doing logical implication. But again, I can build it out of all the other ones. Now, this is going to blow y'all's mind. There's 6 2 input gates up there, and one input gate up there, right? I claim that I can build anything I want out of all of those 7 things. Okay, and that's maybe not too hard to think that, yeah, that definitely can do that. How many of them can I get rid of off of the list and still have a set that allows me to build anything I want? Okay, so which ones could I get rid of? And there's multiple answers to this question, by the way. So for example, I could get rid of the NOT gate because I can build it out of a NAND gate where I just tie both inputs together. That works. Maybe seems like cheating, but this is going to blow y'all's mind. The NAND gate by itself can build everything else. You just need to use a bunch of them and be clever about it. Okay, the NOR gate can also do that. Okay, so the NAND gate is what we call a universal gate, meaning that everything, any other gate, 2-input gate, you can build out of a crap ton of NAND gates if you're clever. No? You guys believe me? Or no? Sure? Ah, believe it or not, no. You can build anything you want out of NAND gates only, but you can't build everything you want out of AND gates only. Huh. Why? Logic. I mean, I'd have to sit down and prove it, right? And turn this into a math class, which is not what you guys signed up for. Or worse, turn this into a logic class. Okay. Yeah, it turns out you can't do it. So, which maybe seems a little weird, right? But yeah. So there's the 6, and we've got the special symbols for all 6, right? And what's the pattern to the symbols? Anything that has the word or in it has a rounded back. Anything with the word and has a flat back. And anything that has the word not in it has a little loop on the end of it. Okay? So that's the symbol set. Good. So questions with that? No? And then the last piece would be, have we figured out, at least theoretically, how we're going to put together the exclusive OR gate? All right. What are the 3 pieces that we're going to build it out of? One NAND gate, one OR gate, and an AND gate. Okay. So get busy getting these things built onto the breadboards. The NAND gates you've already done. Okay. So build 2 more things. We? Okay. All right. So preview of coming attractions. Where we're going to go with this is well, a couple of things. If I've zoomed out to the point of logic gates here, then I can do a couple of things. I can start to think about how I'd put together lots of gates to do, for example, computer arithmetic, right? So how do I do arithmetic with numbers on a computer? Well, we got a little bit of a problem, because how do you add when the numbers that we've, like, what kind of numbers are we dealing with here? Just zeros and ones, right? So we have to relearn how to do arithmetic is essentially the problem. Okay, and in particular, what kind of arithmetic is this? It's binary arithmetic, or base 2. Has anybody actually done base 2 arithmetic before? A little bit? Yeah? Okay. All right. So there are two answers for how base 2 arithmetic works. One is it's super complicated and horrible and you're all going to hate it. The other is it's really like base 10 arithmetic, just pretend you only have 2 fingers. Okay? Or pretend that you use your fingers a little bit differently. Okay? So, I'm going to write down a funny joke. This is sort of our obligatory dad joke for the day. Okay, so why is this funny? Like when you look at that, what do you see? Yeah? 1, 0 is actually 2, okay, in binary. All right, so you look at it and your mind immediately thinks 10, right? Because, well, that's the arithmetic system that we use. But in binary, it actually means 2, okay? So that's where we need to go next. And for that part, we'll switch over to the iPad so I can write. Okay, good? All right, so let me switch to the iPad here. Okay, and let's start talking binary or base 2. Okay, so to motivate this, let me ask you guys the following question. Let's pick a number, and I'm going to choose the number because if I let you guys choose it, you'll choose inappropriate ones. Okay, let's choose this number. That's a great number, right? 1832. Yeah, the founding of the college. Okay, and we're not that far from 2032, the bicentennial. Wow, right? All right, what does that number mean? Okay, when I say what does it mean, forget the fact that it has anything to do with the founding of the college or whatever. Just mean, what does it mean as a number? How do you decode this? Yeah, Jacob. Mhm. Well, eight's first, but yeah. Okay, so, but this number is not in base 2, is it? No, it's in base 10. Okay, so what does the 2 mean here in 1832? He's in the which place? The ones place. Okay, so we use a place value number system, right? And so we have the ones place, the tens place, the hundreds place, the thousands place, and I'm going to rewrite that a little bit as 10 to the 0, 10 to the first, 10 to the second, and 10 to the third. Okay, so the brilliance of the Hindu Arabic numeral system that we use, right, is how many digits do we have? Sorry, how many digits are there in total? Not in this particular number, but there are 10 digits, right? 0 through 9, right? Do I need any more symbols than that to write down any number? No. That's the brilliant part of the Hindu Arabic system, right? Is that I only need those 10 symbols, but then the relative position of multiple symbols tells me their value, right? We call this place value arithmetic, right? So how do I know that the 2 means 2, but the 3 here really means 30? Because of the position, right? And that's all that matters is just the position of the numbers or the digits. And then the other brilliant part is what about if I need to skip a position? we've got a symbol for that, and it is the symbol for 0. Okay, so 1832, right? And think back, maybe you guys don't, maybe it's been too long, but you guys remember in elementary school they made you think of this as 1,832? Yeah? Okay, and it may have seemed like, yes, of course it's 1832, right? And I'm belaboring the point here, but what we really want to think of is that the 1 or the 8 or whatever are in a position that corresponds to a particular place value. Now, in elementary school, right, you called this the ones, tens, hundreds, and thousands place, and so on, right? We can keep going as much as we want. But below 1, 10, 100, and 1,000, what have I written? I've written this in exponential form, okay? But notice, therefore, the pattern, right? The ones place is 10 to the 0. The next place is 10 to the first, 10 to the second, 10 to the third, and so on. And the reason that I've written everything in terms of 10 is because this is base 10 arithmetic, right? If I want to do base 8 arithmetic, then I would have 1, 8, 8 squared, 8 cubed, and so on. And I could do that if, well, imagine I came around and cut off 2 of everybody's fingers. Just, right? Would you count in base 8 then? No. Okay, well, what about if every human was born with precisely 8 fingers instead of 10? Do you think we would have evolved to count in base 8 instead of base 10? Maybe. Okay. Yeah, and that's maybe the likeliest explanation. We happen to have 10 fingers, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Makes sense? Okay. Although I should point out that not every culture that has developed a place value arithmetic system has done it with base 10. Okay, so what are the other ones that you know of? Yeah, the Mayans, they did it in base, do you happen to know? It is base 20, yes. Okay, so Mayan civilization, completely independently, obviously, of the old world, if you will, had a base 20 arithmetic system long before the Spanish showed up. And all of the old world ones were base 10, but there are traces of sort of other bases even today in our languages. For example, in English, how do we count? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then suddenly what happens? Yeah, 13, 14, 15, 16, right? We switch systems at 12, okay? Now, at least in English, 12 is a unit that we use a lot still, right? For eggs, for example, right? Or cookies or donuts or something. We buy those things by the dozen, not by the 10 or the 20. Okay, so there's that little trace, if you will, of sort of a quasi non-base 10 system. And in other languages, so like let's take, for example, French versus Spanish. And this is kind of mind-boggling to me how this happened. Okay, in Spanish, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then what? 11, 12, 13, 14, 15, 16. It switches from 15 to 16. But en français, what is it? 10, 11, 12, 13, 16, or yeah, 16. No, it's not D6. It switches from 16 to 17. Okay, and the fact that Spanish and French are different about that, I'm not sure how that happened. Right? So do you guys see though, like, why would I expect Spanish and French to both do it the same way? Yeah, because they both derive from Latin, right? and they're not really all that far from each other. So 15 says, right, is 16, and then 17, 18, 19, 20. Now, French is also infuriating because how do you say 85, for example? 4 20s and a 5, right? Because that totally makes sense. Anyway, okay, so where we're going with this, right, is not just to talk about counting in other languages, right? There's really a point here, which is we have to deprogram ourselves from this way of thinking and reprogram ourselves where instead of tens, we're going to have either 2 or, and this is really going to blow your mind, 16 in a couple of instances, okay? And that's where we will get super busy on Monday, okay? All right, have an excellent weekend. Don't have too much fun.